take a step down, then it's a decreasing interval. And if Fred walks level, that's a constant interval. If this is my function, here's what it looks like as Fred moves from left to right. Just like this. When is Fred increasing? Over what interval is he increasing or stepping up? As I move from left to right. Over what interval is the function increasing or moving up? We got 3 of you? No? Yeah. He's always increasing. So as I move left to right, function Fred is always increasing. So what's the interval that we're increasing over? Well, it would be negative infinity to positive infinity. When is it decreasing? Well, when is Fred stepping down as he moves from left to right? You can't go right to left. Hands up, please. Can you tell me what our decreasing interval is going to be? There you go. There's none. When is it constant? Hands up, please, if you can answer that. Nope. Never. He's never constant. He's never flat. Now the next one up is the function values. Looking at this, it's asking you, when are the function values, or the f of x, when are they greater than 0? Look at this graph. The function values are the output values or the y values. For what x's is the function greater than 0? For what x values is the graph greater than 0? So close. We said 1 to positive infinity. You are so close. There's a little bit of typing up you want to give. Now, and I'm going to tell you this. This, what goes here? Parentheses. Because where is the function equal to 0? Hands up, please, if you can answer that. We're going to bounce out of this last one. When is the function equal to 0? Over what interval? Just at 0. So we'll put a bracket with the 0. Now, when is it less than 0? Hands up, please, if you can answer that. Over what interval is the output values, or for what x's are the output values or y values going to be less than 0? I've got 1, 2 of us so far. 3, we can do better. What do you want to say?
0,
You're so close. I don't know why they don't fix this. Who could tighten that up? Lower bound, then upper bound. Not the other way around. So it's negative infinity up to 0. Lowest value, then higher value. There's some questions we are not going to be able to answer. One of them, one is the zeros of this. How would you find the zeros of a function? Zeros are the same as the x-intercepts, and the way that you find it is to set y equal to 0 and solve it out. So this would be y equals x. Well, wait a minute, set the y equal to 0, so 0 equals x. That means the zeros are the coordinates 0, 0, or x equals 0. There's some debate, I guess, as to whether when 1 is appropriate, but if it's asking for the zeros, you could say it's at 0. If it's asking for the x-intercepts, that's an ordered pair. Now, what are, and again, here's another one, hopefully this isn't too much for us, maximum values. Now, that brings us to a good question. When we say our maximum is infinity, I always say, give it the apples test. You have infinity apples. No. Like no matter how many times you think you're holding enough apples to constitute, like if I said go to the orchard on the side, come back with infinity apples, right? You come back with like a giant handful. Like you literally can't hold any more. There's no apples left on the trees. Have you picked infinity apples? No, because someone would need to say, well, I've got one more than you. Is there a maximum? And here's your reasoning. The function is unbounded above. What does that mean? There's no ceiling on it. It always is getting bigger. Now, how about the second piece of this? Are there minimums? Apply the same logic. Hands up, please, if you can tell me what the minimum for this function would be. Y. What's your... There you go. Questions on that? Now, inverses we're actually doing today constitutes about 6 to 8% of the Common Core exam. Is the function odd, even, or neither? Well, we haven't dealt with that yet, but we have dealt with these two things. Who remembers what an onto function is? Does anyone recall from last time that we met what an onto function is? I'll tell you this. A line is an onto function, but a parabola is not. Does anybody remember why the parabola was not an onto function?
I don't know if this is correct, but it doesn't always increase the same interval.
No? Go back and look then. You have your note packets, go back and look. What's an onto function? We definitely reference it. Right? On the second day. Lines. Yeah. Look at, I think we talked about it on page 7. I know we discussed it in class on page 7 stuff. Did anybody write down what an onto function was? No? The domain for both of them is all real numbers. An onto function uses every available output value. Does a parabola, think of y equals x squared, does that use every available output value? Yes or no? Hands up, please, and you can tell me an available output value that y equals x squared will not use. Hands up, please, and you can tell me what available input or available range number is not arrived at if you graph out y equals x squared. You got seriously one person, two of you? What are you going to say? Any negative number. Any negative number is available and not used. Is this graph onto? Let's give out our reason. How about a one-to-one function? I don't think you know what that is yet. A parabola is not a one-to-one function, but it is a function. A one-to-one function passes the vertical line test and the horizontal line test. And we'll get into what that means later on. Looking at that graph, is that graph going to pass my vertical line test? Yes or no?
Yes.
Does it pass the horizontal line test? So let's give that down. We'll go into what that means later. Remember how we said the lazy Larry definition of these things is fails the vertical line test, horizontal test. The Reg is okay with taking it. I hope that you give more. We can't answer this, or this yet. Here's another one that's going to be a little bit funny because the answer is so obvious that it'll stare you and slap you in the face and you won't see it. As x goes out to positive infinity, what are the y values going to? So let's say you are function Frank. You're sliding along, positive infinity goes out to the right forever. What are the y values or function values going to as I go out to the right forever? We got one person that can make a conjecture. That's terrific. My function values go out to positive infinity. Now, what happens as function Frank moves out to the left forever? Was it function Frank or function Fred? Fred, I'm sorry. This is reserved for trig graphs. Now, you're done. That took us 5 minutes, maybe, to go through and get done. A little bit more. Let's bounce over, please, to this. There's 3. Now, you can have your note package out, please, and open to, what page did we leave off on? 19, is that, if I remember right. Is that correct or no? 18. Someplace on the margin, you're going to turn this over. There's more in the middle. In the middle? Higher? This right here, this is what we need to make sure, maybe someplace on here, we need to get these 3 things down. Everything you need to know about inverses. There's 3 different ways to go about taking an inverse. An inverse of a relation or a collection of points is going to cause the point AB to become the point BA. You transpose the coordinates or switch them. So, if the original contains the point 1, 8, the inverse would contain the point 8, 1. That's the first thing. The second thing is, if you're going to graph it, you take the original and reflect it over the line y equals x. Now, this was personally offensive in the first class yesterday, because they go, well, how are we supposed to know what the line y equals x looks like? Why did I have a minor aneurysm from hearing someone say, well, how are we supposed to know what the line y equals x is like? It's your function of the weight. How can you not know what it looks like? You just spent 25 minutes analyzing. It would have been easier if you just came up to me and kicked me in the throat. Look at number 3. So we've dealt with a bunch of points. We've dealt with a graph. Now for an equation. In an equation, to get the inverse, switch the x and the y, and you solve for y. The big thing that you need to know is this. If the original function that you're graphing is 1-to-1, so it passes the vertical line test and the horizontal line test, we now know that the inverse will be a function without finding anything about it. If the original is 1-to-1, we know that the inverse will be a function without finding. Who can give me an example of a graph that would have an inverse that's not a function? Something that would fail or not be 1-to-1. Who can give me something that is a function but not a 1-to-1 function, thus the inverse would not be a function? We got 1 person, 2. What do you want to say?
Y equals x squared.
Yeah, any parabola, any quadratic. You're going to have to, we'll restrict the domain, and we'll see that as we do the math. We have all of these 4 things down. Make sure you memorize these, make sure you have these down. This, if I spent the time typing it, I can assure you it's important for you to get down. We're going to be referencing the same graphic the entire year. Now, let's bounce over. Function of the week. Inverse operations undo previous operations. So, easy example, if the operation puts on the sock, the inverse would take it off. Over here, if my original function adds 2 to my input, what would the inverse have to do? Hands up, please, if you can tell me. The job is to undo it. Take your input and add 2, then you go through and subtract it. Now, it's not that easy, but that's the concept. You have to think of it as undoing the other. And there's almost too much we give you. And, well, we'll even say this. Based off of what you have down already, look at that relation of points. Oh, here's another thing that you need to know. This notation here means F inverse. Now, who can tell me, if that's my F of X, who can tell me one point that would be on F inverse? Look at the original, the top of the page, it gives you this F of X. You already should have listed this out. Hands up, please, if you can tell me one point that would be on F inverse of X. We'll wait for 6 or 7 of you. And a P, what would you say? 2 comma 1 would be one of the points on the inverse. Okay, well, ask what's another point that's going to be on the inverse.
700.
And AJ, what would the last point on the inverse be? All you're doing is switching the x and the y. The x's are referred to as the inputs or the what? What's synonymous with an input? What's the other word for it? Starts with a D? There mumbles. Domain. And the output is the range. So if f of x is a set of ordered pairs, then the inverse is found by going through and switching the x and the y coordinates. The domain of the original is going to be the same as what in the inverse? Hands up, please, if you can tell me that. The domain of the original is the same as what in the inverse? 2 people? Range? Perfect. And the range of the original is going to be the same as the domain of the inverse. Here's my first one. Now, this, keep in mind, this was for this note stays for Regents level kids, so they need to see it a little bit more broken down. Some of it is fine. Next, fine. Looking at this original f of x, the original function is telling me to take 2 times my input minus 5. Look at what's getting done on your input. If I plug a number in, the first thing that would be done is that I multiply it by 2 and then subtract it by 5. So I multiply my input by 2 and subtract 5. What do you think the inverse is going to do first? And it's okay, you're going to stumble in the beginning. What do you want to say? Subtract by 5? Close. Add by 5 and then do what afterwards? Terrific. So we need to take that, add 5 and divide by 2. What's that going to look like as a function? Well, it would be the quantity of x plus 5, that's me adding 5, and then divide it by 2. Now that's not how you go about finding an inverse algebraically, but it's that concept. You're undoing the operations in the opposite order. So if I were to go through and plug in 8 into the original function, go through right now, please, plug in 8 into the original function. Go through right now, plug in 8 into the original function. And Marissa D, let us know what you get as your output. 2 times 8 going to give you? 16, and then subtract 5 from that, and you have 11. Now let's go in and plug 11 into the inverse function. So Sean, Al, what would you get when you plug an 11 into the input function?
One size, 16 value comes in.
See how we ended up with the original? That's how you know they're inverses. Now, let's bounce over, please. Who can tell me what my first step in finding the inverse is going to be? If this is my equation, y equals 2x cubed plus 7, what's the first step in finding the inverse of this equation? I'll give you a hint. You literally spent about 2 minutes writing it down at the beginning of the class. If you don't know, go back and reference that list of 3 things. What's your first step in finding the equation of the inverse? Sabrina? What did you list out?
Point A, B becomes
Nope,
B.
sorry, for an equation. That was the third thing on your checklist we did at the beginning.
The equation we switch x and y on the
Stop right there. First thing up, switch the x and the y. Very first thing, switch the x and the y. So Riley, what is this equation going to look like when I switch the x and the y?
2x cubed equals y plus 7.
No, these guys switch. X is equal to 2y cubed plus 7. So I did my first step. What's the next thing after I switch the x and y? Joyce, what did you have down? So what would you do if you want to get the y alone in that? Nope. Take care of what's furthest away first. Subtract the 7. So I'm going to have x minus 7 equals 2y cubed. What happens next from here? So what you do next? So I've got x minus 7 over 2 is equal to y to the third. You can tell me what we would do now to solve for y. You take the cube root of both sides. Now, when I do that, the algebra purists will write it out as the cube root of x minus 7 over 2 is going to be equal to, well, some people say, well, now I'm left with y. Here's the problem. This is a special kind of y. Compared to the original, this is the inverse. What do we need to tack on to this y to denote that it's the inverse of the previous y? We got 2 people who can remember, 3. That little minus 1 here, or y inverse. Questions on that? The process is the same every time. Now, and remember, you're going to be referencing those 3 steps constantly. So if you want to go back, you can put sparklers around it, streamers, Christmas lights, I don't care. You need to be able to remember those 3 things with that one-to-one piece on it as well. That's what's so important. Looking at what I have, what if the function is given as a graph? Well, that's my graph of f of x. I need to figure out how I would take the inverse of it. So, Marissa T., what would you do to take the inverse of this graph? What did we write down for taking the inverse of a graph? So I'm going to sketch out the diagonal y is equal to x. That's the first thing that I would do. And you do it very, very lightly. That's the diagonal y equals x. Now we get into this piece where we're going, all right, well, if that's the case, now here's one that I'm pretty sure Dr. Welker didn't teach you well. Who knows what a lattice point is? So you know those, but you don't. They give you all these. Lattice point is, see these gray grid lines? A lattice point is a point on the graph that occurs where the grid lines cross. How many lattice points are there, easy ones, are there in number 3? Or sorry, in f of x? How many easy points, how many easy coordinates can you pull out? 3. There's one here, here, and here. Now, this was a little disheartening from the other section. You need to be able to tell me what the coordinates are. And again, coming from geometry honors, it's a little disheartening the number of people who would tell me that this is the point 0, -1. This is -1, 0. This as a coordinate is 0, 2. And this as a coordinate is 1, 4. Now, there's multiple ways that you can do this. If I'm reflecting it over the line y equals x, you can do it visually or you can do it by coordinates. When I talk about visually, this is what I mean. If this point here looks at itself in this mirror, where will it see itself? Well, this point here looks in the mirror. It's perpendicular here, so where does the point have to go? There. Now, the safer bet is to go through and to just transpose the coordinates that are given. That's why I labeled them on the original f of x. So Kirsten, what would you go through and say is another ordered pair that would be on the inverse? So let's go over 2 and up 0. That puts me there. My last point, Molly, what do you say? So go over 4, up 1. Do I put arrows at the end of this? No. And label it as the inverse. Remember, this is the notation for what we said previously. That's the inverse y equals x. Now, is this a function? So looking at what's there, look at the original f of x, and Ben, is that going to be a function?
Yes.
Is the inverse, well, we can even do this without answering it. Is it a function? Yes. And we can say more. What type of function is it? We'd say that this is a one-to-one function. So if it's a one-to-one function, what do we know about the inverse? The inverse will also be a function. The original is 1-to-1. The inverse will also be a function. Questions on that? Every relation has an inverse, therefore every function has an inverse. However, every inverse is not a function. Let's give an example of that. Who can give me an example of an equation where the original is a function and the inverse will not be a function? Who can give me an example of a graph where the original is a function and the inverse is not a function? Got 3 people, 4. We've done that. We literally had a special problem. Yeah. Is that a function? Why do you know that the inverse won't be a function? Because it's going to fail the horizontal line test. I'm going to graph. Which did you say was y equals x squared? Okay. So that would look like this. So I'm going to graph out y equals x squared. It looks something like this. That's a terrible parabola. Here's my diagonal. What is the inverse then going to look like? Well, when this bottom piece is reflected over, it drops down like this. When this top piece is reflected over, it looks like this. Here is f inverse of x, and here is f of x. The original is a function, the inverse is not. You have to be able to give me counterexamples. That shows me that you're able to correctly analyze the situation. Questions on that? Now, we're actually going to get to something else, so we might as well discuss it now. If I look at this graph, looking at what's there, that is not a function. However, that is a function. It's going to have an inverse. It's not a function. The problem is, if instead of looking at the whole graph, I just look at a specific piece of it, it is one-to-one. From where to where can I look at this graph and have that piece of the graph be one-to-one? One possible answer is from 0 out to positive infinity, which would be this window here. If I only look from 0 out to positive infinity, is that portion one-to-one? Okay. Who can give me another interval that I could restrict this to so it would be one-to-one? Two people, seriously. Oh. Negative infinity to 0 also. You could pick either one. That means I'm just looking at the left half. You need to keep that in mind for the tougher questions we're going to deal with. First one up, though, this one should be kind of easy. Go through, find the inverse, and is the inverse a function? So go through and do those three things right now. Thomas, what would you do to find your inverse?
You add 2.
Careful. Here's what I start with. F of x is the same as what? Anybody tell me what I replace the f of x with, Sean? Y. Okay. So if we have that, what's your first step in finding the inverse?
Switching the x to y.
So what's it going to look like when I do that?
X equals 3 minus 3.
Now can you solve for the y?
Add 2. Then divide by 3.
Now, I could say that, but that's really poor notation. What did we name the function in the original? Or original, excuse me. F of x. So we would state this out as f inverse of x equals x plus 2 over 3. Is that going to be a function? Or is the inverse going to be a function? I know whether or not it's going to be a function before I did any of that garbage in finding it. Sam, is the inverse going to be a function, yes or no? Yes. Why? Who can be more specific? What was the original, Sam? The original is a line. So we'd say, yes, f of x is a line and is. What property do I know that allows me to determine whether or not the inverse is a function without actually finding it? Who can tell me? 2 people? 3? Yeah. It's. Do I need to put in a parenthesis here? Or an apostrophe here? Yes? Okay. If it's wrong, I'll have Mr. Paul look. I thought it was for it is.
It is, so it should not be.
It should not be there?
It
Okay.
shouldn't be there. No,
Wait, so wait.
because it would be
Oh,
saying, so
you're
it is.
But isn't it possessing something too? It's the possessive version of it? I'll send this to Mr. Paul. These are the things that we argue in. Math is so beautiful because you don't argue over math. There's one way to do it. But English is like 7,000 rules. We don't know if our English is right. And that's not how you spell function either. We'll let it go. Whatever. You got the idea. Now, here's our problem. Watch what happens when we do this out. I'm going to answer the second part before the first. Before I find the inverse, I'm going to say, is this going to be a function? Hands up, please, if you can answer that piece of this. We have two people. Emily H., what do you say? Would this be a function? Why? Which type of graph is that going to be? So what would you say? Let's say no, the inverse won't be a function because the original, can you finish that out? The original will be a function, but it's not. It won't. What type of function does it need to be in order for the inverse to be a function? No? Sam? It has to be one-to-one. So since this is not, because the original isn't, I know that that's the correct use of isn't. There is the parentheses there. Because the original isn't one-to-one. So again, let's go through and do this out. So Connor, what would your first step be in order to go through and determine the inverse of this equation?
You switch the x and the y. Well, first you turn out the x and the y.
Okay, so I'm going to write it out as y equals the quantity x minus 7 being squared. Now what would you do next?
Then you switch the x and y.
Okay, so what would this look like then?
X equals bracket 5 minus x.
Okay, what happens next? Go. You want to get that y by itself. How can I get the y alone? We got 1, 2, 3 of you. Big decision, you're going to ruin someone's day. So, John, has your day been ruined yet? Wait, has your day been ruined? No? Does this ruin your day? Good answer. Good answer. All right, so what would you do to get the y alone? No? Sean K., what do you think? Let's take the square root of both sides. Now, here's the question, and all of you are going to screw this up. Who took the square root? Was it given to us, or did we insert it in? When you insert it, it's a plus and a minus. The reason being, you have to, when you're taking the square root of a number, there's a positive root and a negative root that you need to accommodate for. Now, when we're doing this, think about it this way. If I told you a number squared equals 25, and you only said 5, would you be right? No. What other number squared gives you 25? Negative 5. Now let's go over here. We still need to solve this out for y. Hopefully this isn't where we get stuck. So this will be the square root of x, then plus a 7 is equal to f inverse of x. So when you graph it out and graph the inverse, it's not going to be a function because this would give you actually a sideways parabola. This is two separate functions. It's the square root of x plus 7 and the negative square root of x plus 7. For the inverse of a function to be a function, the function must be 1-to-1. A function is 1-to-1 if each y value has only one x value associated with it. Look at 5a. Corey, is that 1-to-1? So what do you know about the inverse? It's a function. How about for the next one? Mickey, is that 1-to-1? Which one? It's one of those two. It's either yes or no.
Yes. No.
Is it a 1-to-1? Is it a 1-to-1 function? No.
No.
Why?
Because it doesn't it doesn't use all possible outputs.
That's for an onto function. Be careful. Who remembers why this is not going to be a 1-to-1 function? That fails the horizontal line test. So this function is not one-to-one. So what do we know about G inverse then? It's not going to be a function. You can find it, but G inverse is going to fail the vertical line test. Yeah, we got one more to do. Here's what it ends up being, and this is terrific. The square root of x plus 3. Now, when we're doing this out, because we're going to arrive at something terrific when we do this. Nick, what would your first step be in finding the inverse? Oh, let's answer the second part. Is the inverse a function?
I'm going to go with,
It's 50-50.
I'm going to go with, yes.
Why? The answer to that's always going to be the same. How do you know that the inverse is going to be a function? Who can help them out? This should be automatic.
Because the first one's a one-by-one.
Yeah. So we would say, is the inverse a function? We can actually answer that before we find it. Is the inverse a function? Yes. Let me see. I hear this. Ah. Now, we could graph this out to determine that. The square root sort of looks like maybe sort of like that a little bit. Shift it up 3. What would our first step be to find out the original? Tommy, what do you say? Okay, so I've got y equals root x plus 3. Keep going. Okay, so what would you write out? What would you do next? And then? Here's the problem. What did we get when we took our inverse? We got a quadratic. What I need you all to do right now is this. Go into your calculators, please. Collectively go into your calculators, please. Go into a new document and let's add a graph. And you're going to graph in the original. We're going to add a graph. You're going to put the original in, which would be the square root of x. Get out of that then plus 3. So you're going to graph root x plus 3. Arrow over, plus 3. Now, we're going to hit enter. You're going to need to reflect that over the line y equals x. So go in. What is it, Control T or Control G? Tab to get a second one. Okay. So get a second graph on there. You're going to graph the line y equals x. I think it's Control T. Yeah. Okay. So now go in and graph y equals out. Delete that y. F of x is the same thing. So you're going to graph y equals x. And now the third thing that you're going to graph is going to be what our inverse was, which was the quantity. Was it the quantity x minus 3 being squared? Is that right? Okay. Now, go in and graph that third thing. So, here's the problem. We gave too much. If this is the original, which part of this is going to be the inverse? Am I going... Oh, yeah, I mean... Remains. Yes. Here. So, which half of this black graph is going to be the one that is the inverse? If this is what your screen looks like, which half of this is the inverse? Is it the left half or the right half? The right half. So this piece here, what we're saying is, here's my original. If I reflect it over, I get this here, and that's true. that means you need to restrict the domain down. So this is my inverse as long as the x value is what?
3 or greater.
Yeah, 3 or bigger. So we would go through and say that this is my inverse as long as x is greater than or equal to 3. There are times where that's going to happen. When you square a root, you can get extra information or lose pertinent information. Now, what your homework is going to be is from that sheet, your homework packet, the one that's posted through Google Classroom as well. So if you don't have a physical copy of it, you can always get one through our Google Classroom. Is this sheet mandatory? No. If you want to, those questions will be available. We have one more day and a review day and then your exam. So do your best. Not for today. Yeah, we just finished day 4. Yeah, we just did day 4. Right?